This video goes over how to use the binomial theorem, which is going to allow us to use combinations and simple patterns to quickly find the expansions of binomials raised to different patterns. So in general, the binomial theorem is a plus b to the n, which is going to be the sum from r equals 0 to n of n choose r, a to the n minus r times b to the r. We can also write this as the sum of r equals 0 to n of n choose r, a to the n minus r, b to the r. All that sum notation means is that you're adding up all the possibilities going all the way from r equals 0 to whatever the expansion on your binomial is. So let's try an example here. We're going to expand the following: x plus 2 to the 5. Hopefully you can visualize if we did this by hand, it would take a long time and there's a lot of algebra. So what we're going to do is use the binomial theorem to expand. So my first coefficient, I'm going to start with n, which is this value right here. So I've got 5, choose 0 because that's my first r value. My a value is this x, so I would have x to the 5 minus 0, and then my b value is this 2, so I would have then 2 to my r, and I'm going to continue along in that pattern. So 5 choose 1, x to the 5 minus 1, 2 to the 1, 5 choose 2, x to the 5 minus 2, 2 to the 2, 5 choose 3, x to the 5 minus 3, 2 to the 3. I'm going to run out of space here. And then I've got plus 5 choose 4, x to the 5 minus 4, 2 to the 4. And then my last one is going to be 5 choose 5, x to the 5 minus 5, and then 2 to the 5. So I can evaluate that on my calculator, which is going to give me 1, so 5 choose 0, x to the 5 times 1, plus 5, x to the 4 times 2, plus 10, x to the 3 times 4, plus 10, x squared to the 8, plus 5 times x times 16, plus 1 times 32, and then simplifying that finally will give me x5 plus 10x to the 4 plus 40x cubed plus 80x squared plus 80x plus 32. Still a little bit cumbersome, but easier than multiplying it manually by hand. The other thing that we can do is we can actually find a particular term of the binomial expansion, which can be important in determining the trends of a function or how a particular graph or distribution is going to behave. So we can use this expression to find the r plus 1 term. So we can use this if there's just one term in a binomial expansion that we want. So here we're going to find the 8th term in the expansion of x squared minus 5 to the 11. So because I'm looking for the 8th term, my r value is going to be 1 less than that, which is 7. My a term is the first term in my binomial here. And then my b term is going to be minus 5, because the definition of a binomial is a plus b. So if there is a negative, you need to consider that as part of your b value. The last thing that I need is my n, which is the exponent that the binomial is raised to, which is 11. And now I can actually find the 8th term. So I know that I would have 11 choose 7, a raised to the exponent of n minus r, or 11 minus 7. And then I'm going to multiply by b raised to the exponent r. So now I've got an expression that I can simplify using my calculator. x squared to the 5, and then I would have minus 78,125. The last thing I'm going to do is put it all together. So I would have minus 25,781,250 x to the 10. So if I was looking for that 10th term, this is much faster, just picking one term in the expansion as opposed to doing them all. Okay. You should also note that the coefficients of the expansion are going to correspond to the nth row of Pascal's triangle, which is a neat connection. If you choose to use that, you can maybe make it yourself a little bit more efficient. The next example that we're going to do is finding a particular coefficient of the term that has a particular power of x. So we know that we need x to the 21. So that means that in my expansion, the x parts are going to have to add up to 21. So let's write out that general coefficient. So I would have 13, choose r. I'm going to have a raised to the n minus r. And then I'm going to have my b value raised to the r. Now, this doesn't matter because it's a number, and this 2 doesn't matter either. So the parts that I'm concerned about are the x cubed to the 13 minus r and the x to the r. I know that this has to equal x to the exponent 21. So expanding and simplifying here gives me x to the 39 minus 3r times x to the r equals x to the 21. Using my knowledge of exponent laws, I've got 39 minus 2r has to be equal to x to the 21. Now I know because the bases are equal, I can set the exponents equal to each other. And this is going to allow me to solve for my value of r, which is then going to allow me to calculate the coefficient. So then I can go back to my original expression, which is right here, and I'm going to evaluate that, but I'm going to use the value of r that I found. So what I have is 13, choose 9, x cubed to the 13 minus 9, and then I've got 2x to the exponent 9. This is going to give me 715 times x to the 12, and then I've got 2 to the 9, and then x to the 9. So multiplying those all out together is going to give me 366,080 x to the 21, which is what I'm asked for. And so that means that my coefficient is just the number that's right here. Okay, we're going to do one more example, which sort of ties back into Pascal's triangle and counting the number of pathways. We're going to find the number of paths through the following letters that spell the word counting. So I'm going to start with C. I know that my next letter has to be O, and there is one way to get there. My next is U, and I've got one way, two ways, and one way. And I'm going to keep adding them up here. So to get to N would be 1, 3, 3, and 1. Hopefully you're seeing a pattern here. And then I've got 4, 6, 4, and 1 to get to the T. Now I have to go back in. So 5, 10, 10, and 5. Going back in again. 15, 20, 15. And then my last at the G's, I've got 35 ways to get to each G, which means that my total number of paths is just going to be 35 plus 35, which gives me a total of 70 ways to spell the word